everyone? Let's go ahead and let's go over it. All right, so you had on page 79 the application 1 and 2. We'll come back to that in just a second. But let's go ahead and let's go over to page 85 and do the not define, but the section review 4 and 5. All right, so number 4, define specific heat. This is the heat required to cause a unit rise in a unit mass of a substance. We'll talk more about that in a little bit. Number 5, what laboratory instrument is used to measure heat flow? So calorimeter is how you say that. It looks like calorimeter, but calorimeter is how you're technically supposed to say it. All right, let's go back to that application process now. All right, so application number 1. In a certain process, 245 joules of work was done by a system on its surroundings. 45 joules of heat was lost to the surroundings. What is the delta E for this system? All right, think back over it. All right, what does delta E stand for? What does delta stand for? Change. What does E stand for? Internal energy. All right, so we're talking about the system and the surroundings. So remember, thermodynamic system is what we're looking at. Surroundings is everything else in the universe, but technically, but for practical purposes, it's the rest of the lab bench or the rest of the room. All right, so in a certain process, so remember, for the equation that we're using for this, we're using work, heat, and delta E. So remember, it's delta E, not too bad, delta, I'm going to ignore it for now. So delta E equals, remember what's the symbol for heat? Q plus W. I'm going to write them over here. So Q and W as well. Make sure that you note your symbols for it or your letters. Alright, so we're finding delta E. Okay, it's going to bother me now. So now I got to fix it. I can't draw triangles very well sideways. Alright, so for this one, I'm finding delta E. Now, it says certain process, 245 joules of work was done by the system to the surroundings. Alright, so is the system losing or gaining energy? If it's using its energy on the surroundings. Right, it's losing it. So, this one is work, so it's negative 245 joules. Remember, joules is the SI unit for energy. So, negative 245 joules, and then it says 45 joules of heat was lost to the surroundings. So, it also lost 45 joules. Alright, so it's heat plus work, so negative 45 joules plus negative 245 will equal what? Right, 290 negative. Now, can I, oh, don't forget your units, joules. Alright, can I leave it just like this, where it says 290, no decimal points? No, why? Just remember this is addition and subtraction, so since this one ends in the 1 spot, and this one ends in the 1 spot, this one has to end in the 1 spot as well. So I have to put a decimal point, otherwise it doesn't count. So I have to make it have a decimal point there. Alright, let's go ahead and let's look at the second one now. What is the delta E for a system of 300 with the decimal point? Joules is heat is added to a system and no work is done. Alright, so it says that I have 300 joules added with a decimal point. Alright, so I probably don't have to put a positive sign, but I don't want to forget that it's positive, so I'm just going to leave a positive sign on it. Plus 0 work. So for this one, just adding it up, it says that it's 300 joules plus 0. Now, 0 technically doesn't have any sig figs in it, so we're just going to worry about sig figs for this one. So since it's 300 plus 0, it just becomes 300 joules as the answer for it. So remember, it's got to be 300 though with a decimal point. Alright, so that's the main ideas for that section. We'll practice it just a little bit more because we have quite a bit of math to go over today. If you read through your homework as you were paying attention through it, you noticed, now equations coming up. Yes, you do. This is a major math-heavy section, so if math's your thing, make sure you read your questions carefully to figure out what am I supposed to be doing. If math's not your thing and you've been struggling with this all year, pay attention and make sure that you're following along so that way you don't get lost. Alright, for your classwork, I want you to copy down the bold terms and their definitions from pages 77 to page 81. We haven't quite talked about specific heat yet, but it won't hurt you to write it down. So pages 77 to page 81. So I want you to copy down those bold terms and definitions 3 times. So there's not a lot, but there is some. So because of that, again, try to work as quick as you can, in about 5 to 10 minutes, to copy down those bold terms and their definitions 3 times each. So work as quick as you can, be as neat, but work as fast as you can to make sure You're trying to get all of them down. It'll help you to write them out. So go ahead and pause the video and go ahead and do that. Once you unpause the video, you can come, well, once you finish that, you can unpause the video and come back. Alright, assuming that you've unpaused the video and come back now, that means that you're done with it. So I'm going to go over the terms and definitions, not just the bold ones, but the italicized ones as well. Alright, so what do we call the area of chemistry that deals with applying thermodynamic principles to energy changes in chemical reactions? Chemical thermodynamics in particular. What's the flow of energy? Thermodynamics. So, well, excuse me, the study of the flow of energy, not just the flow of energy. Thermodynamics. The flow of heat energy, or that transfer of heat energy, is technically just heat. Alright, so what is the ability to do work? Energy. Alright, what is the law that says that energy can neither be created nor destroyed? Technically, there's two different laws you can put for this. So, law of conservation of energy, and then it's also restated as a mathematical statement of the first law of thermodynamics. That's a practical application of the law of conservation of energy. So, law of conservation of energy, but then it's put in a much better version with the first law of thermodynamics. So, either one works. Alright, what is the energy of motion? Kinetic energy. What is the energy associated with the position of an object relative to the forces upon it, like pulling back a rubber band? Potential energy. Alright, what do you call the portion of the universe that is being studied in thermodynamics? The system. What do you call everything else? Surroundings. Alright, so what does E stand for? Internal energy. What is internal energy? The sum of all the possible forms of energy of all the ions, atoms, and molecules in a system. Can you see internal energy? No, but you can see the changes and that it causes. Like whenever you see the wind blow, you can't see the wind directly, but you can see maybe the dust in the wind or leaves in the wind or how it's blowing through the trees. You can see the effects or the changes it causes, but you can't see it directly. Alright, what's the term? What's the term that refers to a value that is determined only by the state of the system? Like climbing a mountain, doesn't matter how you got there as long as you're there. State function, good job. Alright, what is the symbol for heat? Q. So make sure that that's a transfer of energy between objects or systems. What does W stand for? Work. Good job. Alright. So, what's the equation for finding the first law of thermodynamics? This one. So make sure that you know delta E equals Q plus W. So that way you can solve it if you see it on a quiz or test. That's a practical application of the first law of thermodynamics. So, you want to note it that way, that this equation is a practical application of the first law of thermodynamics. So make a note for that. What is the SI unit of energy and energy transfer? Joule. Alright, so now whenever we're working with this law, we look at it from the view of the system. So if heat is being added to the system, is it a positive value or negative value? Positive. What if it's losing heat? Is that positive or negative? Negative. Good job. What if it's gaining work being done to it, like being compressed as a gas? That's positive. What if it's doing work on the surroundings, so pushing up the pistons or something like that? That's negative. Alright, so what is defined as the internal energy plus the product of pressure and volume? So what's defined as the internal energy plus the product of pressure and volume? Enthalpy. What state of matter do we use enthalpy for in particular? Gases. What symbol do we use for enthalpy? H. Now remember, typically delta E and delta H, that's not an H. Delta H for solids and liquids are typically approximately the same value, because since this is defined as the internal energy plus the product of the pressure and volume, the pressure and volume of a solid and liquid doesn't really change. So because of that, basically, if you have a solid or a liquid, the internal energy will the change in internal energy will equal the change in enthalpy. You only really work with enthalpy with gases, and we'll talk more about that later on. But since these two are related, your book just starts using this symbol to refer to internal energy. And then also, since it affects gases more, because it uses the pressure and the volume. Alright, so what do we call a type of reaction that, so thinking about endothermic versus exothermic in particular. So what type of reaction is summarized by the idea of the reactants plus the products, reactants plus heat equals the product. So it has to use heat in order for it to react. Is that endothermic or exothermic? Endothermic. It has to absorb heat. It has to use it as like an ingredient for it to make its product. Alright, what if it's like the reactants? It produces heat plus the product. So as you have your reactants react, which sounds weird, but as you have your reactants react, they also make heat or give off heat, plus they're making their products as well. So what type of reaction is that? Endothermic or exothermic? Exothermic. So which one is gaining heat? Endothermic or exothermic? Endothermic, because it has to absorb heat or gain that heat in for it to make its product. So it's absorbing heat. So because of that, would the delta H for endothermic, would it be positive or negative? Be positive. Good job. Now again, when I say delta H, I mean delta E, so internal energy as well. So delta H is a more specific one talking about internal energy, but then also for gases specifically. Alright, so for an exothermic reaction, is it losing or gaining heat if it's producing heat as a product? Or giving off heat as a product? Right? That's negative. So negative delta H, it's losing heat, it's giving off of it. Alright, which one will typically feel colder to your touch whenever you have that reaction? Now remember, that doesn't mean like just metal, oh it's cold, it's endothermic. No. Okay, so I kind of half gave it away. But what do you call that type of reaction whenever it feels colder to your touch? Endothermic. What's the one that feels hot to your touch? You don't want to touch it because it's giving off that heat. Exothermic. Alright, good job for it. So make a note, you want to know all those ideas for it as well. Alright, so we talked about specific heat, I think a little bit in heat yesterday. So we'll go ahead and we'll get back into that. So go ahead and look over on page 81. If you weren't following with me in the textbook, make sure you go ahead and you get that out. So that way we can start talking about heat and heat transfer. We kind of left off of this yesterday on page 81. Alright, so thinking about it with heat and with heat transfer. So again, starting back from this side, so just don't forget, endothermic, it absorbs heat, so it's gaining heat, so delta H and delta E is positive. Typically your book writes it as the reactants plus heat, because remember Q stands for heat. So reactants plus heat equals the product. An example of this would be like cooking food, because your food has to absorb that heat for it to cook on the inside and to have that chemical change. Example, for exothermic, it releases heat. Typically it feels hotter to you. The delta H and delta E is negative. And so your book draws it out, or your quiz and test will sometimes show it as reactants. It will produce the products plus heat. So like lighting a match or lighting a coal on fire, as it's burning, it's giving off extra heat. So that's the differences between the idea of cooking food or just burning something. It's the idea of the coal or the mat is giving off energy. It's not changing it on the inside of it. It's just turning to dust, basically. So that's an exothermic reaction. Alright, heat. Your book wants to go from an area, your book points out that heat wants to go from an area of higher concentration to lower concentration. It wants to get that equal point of thermal equilibrium. Now that's not mentioned in your book, but if you want to write it in there, you can. It's not going to be quizzed or tested, but just make a note of it. So, thermal equilibrium wants to be balanced out. So remember, heat's measured in joules, and it flows from higher to lower temperatures. I use this picture in physical science because what would happen if you touch the hot stove? You're going to have the heat from the hot stove get transferred into your finger or into your hand, and so because of that, you will burn your finger if you touch a hot stove. And that's the reason why, because the heat is moving from an area of higher concentration to a lower concentration. It doesn't burn you or give you frostbite because the heat got sucked out of your finger. That's not how it works. It's the idea of too much heat is being transferred from the stove into your hand. We talked through this yesterday with the water and the glass as well. This is another reason why glass or an ice cube melts. Is because as you have your cup of ice, that you have the ice cubes on the inside. Now, the ice cubes are absorbing the energy of the heat of the water around them. Now remember, from the view of the ice cubes then, if the ice cubes are our system, are they losing or gaining energy if they're absorbing energy to melt? That's endothermic because they're absorbing energy. So we would call that an endothermic process. because it's absorbing energy. Now it's not a chemical change, it's not going from it's not changing from water into something else, but it is an endothermic process. That's the idea of, okay, this is going from one state of matter into another state of matter, so it's absorbing energy, so we would call that an endothermic process. Not endothermic reaction technically, but endothermic process. From the view of the water, is the water losing or gaining energy? If it's giving up energy to the ice cubes, it's losing it. So again, we would call that an exothermic process, not exothermic reaction, because it's not actually reacting to anything, but since it's losing energy to something else, we would call that an exothermic process. Alright, just make a note though for the ice cube. So as they're absorbing energy, they're taking the energy or the heat from the water around it. So as they're absorbing the heat, the ice cubes will start to melt. So they're taking the energy and they're using it to break apart their bonds. They're still water, so not chemical change. So they're breaking apart their bonds, but they're going from a solid to a liquid. Remember, a liquid has more energy than a solid. So it's going from a solid to a liquid state. Whenever it does that, since the water around it is losing energy, that's how come your glass will get colder whenever you put ice cubes in it. So that's the example of heat always goes from high temperatures to low temperatures, and that's why your overall glass temperature starts to drop and decrease down. It's not because the ice is spreading the coldness on the inside. That's how little kids, that's a lot of how we describe it for little kids, but that's not technically what's happening. Is you have the ice cubes, because they're absorbing the energy around them to melt, that's why the temperature of your whole glass goes down. It's because it's going from a high temperature overall of your glass to a lower temperature. Alright, so just make a note of that. So your book's describing this for you. Alright, so talking about this with specific heat. Now your book walks you through the equations to how to find the temperature difference. That makes more sense in a minute whenever we talk about calorimeters, so we're going to talk about that more in a second. Alright, so specific heat. Make a note of what specific heat is. That some substances require very little energy to change their temperatures, while some substances require a lot. Water relatively requires a lot of energy to change its temperature, which is a good thing. So you don't have this chart in your book. This is from physical science, if you remember it. So if not, it's okay, don't worry about it. But this is one reason why I grabbed it. Your book has a chart. Wow, I must have touched my necklace and got chopped all over that. Hang on, I'm going to clean that off real quick. Alright, so you'll notice that water, that it has a higher specific heat. That water, it has 4.18 joules per gram degree Celsius. Now, if you're looking at the chart in your book, you'll notice that it has listed as well water 4.18. You don't have to memorize that, but you probably will, just because we use water so much, particularly with calorimeters. So that's one reason why we use it. So while you don't have to memorize it, you probably will. So if you just want to go ahead and just make a note to just start working on it, you can, but you don't have to for it. So make a note, specific heat is given a letter of lowercase c, so make a note for that. So not capital C. Capital C, if you remember from physical science, is heat capacity. So it's a different substance or different term. So just be careful, lowercase c. I'm not going to sit there and quizzes and tests and go, is that capital C or lowercase c? But do make sure, though, that for your equations, you don't want to accidentally confuse yourself. So, specific heat, this is a substance, this is the heat required to cause a unit rise in the temperature of the unit mass of the substance. There's one equation that you use for this, but we use it in two different forms. So, the first version the book gives you is Q over M delta T will equal lowercase c. Alright, what does Q stand for? Heat. What does M typically stand for? Mass. What does delta stand for? Change. What does T typically stand for? Temperature. So that's basically the definition of specific heat. It's the heat required to cause a unit rise in the temperature of a unit mass of the substance. So in order to cause the temperature to change per mass of the substance. So you'll notice that the unit for this is joules per gram degree Celsius. Typically, we use Celsius with this. Now remember, you might think, well, wait a minute, why can't we use Kelvin? You could, because the degrees are the same, but since we're measuring temperature, remember what temperature scales do most nations use? Celsius. Now, you're right, you're working with gases, you want to use Kelvin. But since we're just using temperature changes, we're just using a thermometer. Most thermometers are in Celsius, and since the degrees of Celsius and degrees of Kelvin are the same, it's just convenient to work with it just in Celsius. So because of that, you don't have to change over. You don't have to change over into Kelvin, because mathematically the change of difference is the same between them. So you don't have to worry about getting on the absolute temperature scale. Using Celsius for these is fine. Alright, so you'll notice that some of them on each chart they're a lot lower specific heat than others. So, like for example, for this one, lead, I don't remember if it is in your chart or not. No, it doesn't. Alright, but lead, you'll notice, has a specific heat of 0.13, while water has 4.18. That water has a lot higher specific heat. What does that mean? Alright, remember that this is the amount of energy that is required to cause a unit mass change per unit degree. So I think I said that weird, so let me try to say that again. So to cause a unit rise in the temperature of a unit mass in the substance. So basically, like if you have water that's 4.18 joules per gram degree Celsius, that means it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. Now, you might think, well, that's not a lot. Well, typically, if you have a cup of water, you don't have just 1 gram of water, you have a lot of grams of water. And so because of that, if you want the temperature to change, you're going to have to relatively add in a bunch of energy. While you have other types of metals or substances, their specific heat is a lot lower. So because of that, like for example, lead has 0.13 joules per gram degrees Celsius. So for this one, you only have to add 0.13 joules to cause 1 gram of lead to raise 1 degree of Celsius. This one's temperature will change a lot faster than water. That's because water is known as a good insulator, because water has to absorb a lot of energy for it to start to increase in temperature, or it has to lose a lot of energy for it to have a decrease in temperature. It doesn't change as fast as other metals or other substances. So, looking at this chart, you'll notice that, okay, if I add in, oh, it's blurry from my angle, I believe it's 20.9 kilojoules of heat is added. Then if you add in that much energy, how much degrees will it change by? So if I add 20.9 kilojoules of heat is added, water will increase only 5 degrees. So again, that's not enough to even hurt you really. So 5 degrees in temperature change if you were to touch it, going from like 30 to 35 degrees. Okay, that's not enough to even really mess with. You might not even notice that. A glass will change by 25 degrees. Okay, you might notice that the glass is warm. Iron changes by 46, depending on where it started from. That's kind of a lot. Lead will change by 160. So again, you might start noticing that and notice, whoa, that's kind of warm. But that's the reason why you have water is known as an insulator, because it absorbs heat, or it has to give off a lot of heat to have that temperature change. And that's probably the reason why it's a stabilizing effect, particularly with our weather. So that way you don't have extreme temperature changes around the earth. Water changes its temperature a lot slower than land around it typically. And that's because water has to absorb a lot of energy before you have that temperature change. Alright, so that's kind of like a side note for it. Alright, so this is the equation for specific heat. Typically though, we don't use it a lot in this form. We want to use it to find Q. So if I want to get Q by itself, what do I have to do? Right, instead of multiplying, I have to divide. So I'll move, instead of divide, I have to multiply. So I will take the bottom and move it out to the side. So M delta T times C will equal Q. So that's where that second equation comes from, right at the bottom of page 81. It's way down there, it's almost on the next page. So this equation and the specific heat equation are the same equation. They've just shifted the forms around. So make a note for that equation. So you end up using both forms of it, but you just have to memorize one equation and then think of, okay, how do I shift it so that way I am finding what I need to for it. Alright, let's work through how to solve this type of problem. So the example on page 82. Alright, so how much heat is lost by a piece of copper with a mass of 50 grams when it cools from 95 degrees Celsius to 20 degrees Celsius? And that tells you the specific heat of copper is 0.38 joules per gram degrees Celsius. Alright, how do I find temperature change? Your book describes to you how to find this, because you want to make sure you get the sign in front of it, the right sign. So because of that, technically we're supposed to subtract the initial temperature from the final temperature. So that's what I'm going to give it to you as delta T equals the temperature of the final minus the temperature of the initial. Now, you might think, well, who cares as long as I find the difference, because the sign in front of it matters. So if I'm going from 95 degrees to 20 degrees Celsius, is my temperature going up or going down? Right, it's going down. So am I losing or gaining energy? Losing, because the temperature is going down. Putting that negative sign, you're going to have to put it in front of it, because if you don't, it'll mess up your problems later. So you want to get into the habit of doing it this way, because if you don't have that positive or correct, if you don't have the correct positive or negative value in front of it, you're going to get the wrong answer. That's the reason why you want to develop that good habits now. So because of that, it's 20 degrees, since that's the final temperature, minus the initial, so 95.0 degrees Celsius. Now again, you might think, who cares as long as I remember my sign? Good habits. Develop good habits, and it'll help you on the wrong one. Alright, so this turns into negative 75 degrees Celsius. So, again, because the temperature is going down, it has a temperature change of negative 75 degrees Celsius. So now we can use this to plug into our equation. I'll leave this one up here. So remember, it's Q equals Cm delta T, this version of the specific heat equation, because we're asked specifically to find Q, or to find heat. Alright, so how much heat is lost by a piece of copper with a mass of 50 grams? So my mass, I'm going to put this in parentheses so that way I don't forget the temperature change. So 50 grams with a decimal point and a second zero. So 50 grams, and then it also says the specific heat of copper is 0.38. So 0.38 joules per gram degrees Celsius. Think y'all can still see this? Yeah, y'all can. Alright, so what I do is I multiply all these three things together to find Q. I'll shift it down so you can see it. Alright, so multiply 0.38 times 50 times negative 75. What do you get? You get negative 1,425 joules. Now, keep in mind, what does this negative sign mean if you're talking about joules? Are you losing or gaining energy? Losing, and that is specific. If you write positive value, nope, wrong. Price for credit lost. Because it's asking you how much heat is lost. So it's lost negative, so it's telling you it's losing 1,425. Now, if you were to write on a quiz or test, it has lost positive value 1,425 because you're saying it's being lost, I'll still take it. But keep in mind that if you're just writing it off as just a number, you want to put the negative sign in front of it, because the negative sign is how you tell me and how scientists tell each other this is losing energy. If you leave it as a positive value, you're telling me it's gaining energy, and it's wrong. So you want to make sure that you keep your signs correct, because that's important with thermodynamics. Alright, so for sig figs really quick. Alright, you will notice that I started off with 95.0 degrees Celsius, 20.0 degrees Celsius. Both of those have 3 sig figs. Because this is multiplication and division, we're going to go off number of sig figs. So 3 sig figs, 3 sig figs. 0.38 specific heat though. So if it's 0.38 specific heat, how many sig figs should my answer have? 2. So how do I fix this? Alright, so you can just write it as 1,400, no decimal point, because remember the decimal point will tell you that these zeros count, joules. Your book kind of cheats, and they also convert it to kilojoules. That's another way of doing it. So if you want to change it into kilojoules and write it as 1.4 kilojoules, okay, that's also fine, but just be careful though. If you do it this way, you're going to have to change your units. So either answer this one or this one is fine, but just be careful that you don't want to accidentally try to do something and take a shortcut and you hurt yourself because you're not being careful. So just make sure you're thinking through everything properly. Alright, so let's practice a little bit more with this. So I know this can be a little bit tricky. Alright. Let me pull up my practice problem. that screen shows up better, so if it doesn't, email me and let me know, but I believe y'all can read that from this point. I don't know if I can make it any more zoomed in for it, but I think that's as close as I can get it. Alright, so how much heat does it take to raise the temperature of 100 grams of water a total of 21 degrees Celsius? So again, just practicing with this. Hang on, I forgot something. So just practicing this. So this first one's kind of it's just kind of just a practice problem. If you want to pause the video to work on it yourself and try to see how far you can get, that would be good for it. But how much heat does it take to raise the temperature of 100 grams of water a total of 21 degrees Celsius? So I'm just telling you, okay, your delta H, not delta H, delta T for this one is just 20.1 degrees Celsius. So that's the change. I'm just kind of giving you a little of the help just for this first one as we practice this. So how much heat does it take to raise the temperature of 100, that's not 100, 10 grams of water, a total of 21 degrees Celsius. Now remember, what's the equation that's using heat, mass, temperature change, and specific heat? I didn't give you specific heat because I know you have it in your table and I didn't want to type it up. Alright, so remember the equation is Q equals Cm delta T. So just plugging in all of your correct variables to figure this out. So, what is the specific heat of water? Again, you don't have to memorize it, but you have a table, but since we use water so much, you probably will. Now remember, it's 4.18 joules per gram degrees Celsius. The specific heat of water, what's the mass in this particular example? 10. I never leave enough room, ever. So 10 grams of water, and then the temperature change is 20.1. Let's probably smack down the middle of the bar. Yep. Okay, I'll scoot it over. We're just going to write the temperature on the wrong side for right now. So, 20.1 degrees Celsius. So, you just multiply these three values together. So, the 20.1 times the 4.18 times the 10, and I'll tell you how much heat in joules you gained or lost. So, for this one, how much heat does it take to raise the temperature? So, if the temperature is going up, should it be a positive or negative value? Positive. Alright, so plugging everything in and solving, what do you get? You get 840.18 joules is what your calculator says, but how do I plug this in proper sig figs? Well, this one has 3 sig figs, the specific heat has 3 sig figs, the temperature change has 3 sig figs, so how do I fix this? Alright, 840 with a decimal point joule, positive value, so you either write it like this, or you can put the positive in specifically. So, if you don't have a sign, it's assumed to be positive. Alright, let's do the next one. Try to work that one by yourself. So, try to solve it by yourself, pause the video, and try to work on it. Alright, assuming that you're still watching this, and that means you've already tried it. So let's go through it. Alright, how much heat does it take to raise the temperature of 10 grams of water from 15 degrees to 67 degrees Celsius? Alright, how do I find that temperature change? Remember, good habits, delta T equals the temperature of the final minus the temperature of the initial. Alright, so 67 minus 15, I'm leaving off the point zeros for right now. So that turns into 52 degrees Celsius, 52.0 technically. But remember, it's going from a smaller number to a larger number. So is that an increase in temperature or a decrease in temperature? Increase. So should I have a positive value or a negative value? Positive value. So I'm going to come with 67 minus 15. It'll help you develop good habits to get that positive sign. Alright, so positive 52.0 degrees Celsius times the specific heat of water times the mass. So the mass again is 10 degrees. Sorry, 10 grams. Specific heat 4.18 joules per grams degrees Celsius. Multiply all of these together, what do you get? So 4.18 times 10 times 52.0. You get 2,173.6 joules. Alright, so looking at sig figs again. 3 sig figs, 3 sig figs, 3 sig figs. How many should my answer have? 3 sig figs. So 2,170, no decimal point, joules. And again, is assumed to be positive if there's no positive sign. Alright, number 6. What is the specific heat of the metal if 412 joules is required to heat 44 grams of the metal got cut off slightly, from 19.5 degrees Celsius to 41.4 degrees Celsius. Alright, so we're finding specific heat. How do I rearrange this equation to get specific heat? Right, so to find specific heat, instead of multiplying by the mass and temperature, I just divide. So I put the equation back in the original form. So C equals Q M delta T. So I just reshifted it around that way. Alright, so what is heat? So the heat is 412 joules divided by the mass. So the mass is 44.0 grams. Alright, temperature change. So it's final minus initial. So it's 41.4 minus 19.5 degrees Celsius. That becomes what? What's my temperature change? My temperature change is, I lost my spot, 21.9. So 21.9 degrees Celsius. I don't think you can see that because of the bar, so I'll write it over here. So 21.9 degrees Celsius. Alright, so how do I solve to find specific heat? So you take the 412 divided by the 44 divided by the 21.9. Because remember, is the top divided by the entire product of the bottom. So you're saying in your calculator 412 divided by 44 and then divided by 21.9. So just be careful how you type it in. Alright, so what do you get for that answer? You get lowercase c, so specific heat equals 0.42756, and then it just keeps going, and I'm tired of writing. So it keeps going to that point. Alright, so how many sig figs? 3. How many sig figs? 3. How many sig figs? 3. So since multiplication and division, how many sig figs should my answer have? 3. So the answer becomes 0.428. Now, I've said it a bunch, but make a note of the units for specific heat. It's joules, I cannot write this, per gram degrees Celsius. So, that's the answer for number 6, for practice problem number 6. Alright, so a little bit farther for it, I'll go just a little bit farther and then we'll stop for it. But make sure if you're confused by this that you email me, that you ask me how to solve these. These aren't necessarily hard as long as you understand what's going on. But if you're completely lost now, you gotta be in trouble. Alright, so calorimetry or calorimeters. So scientists, what they'll do is, since they know with the first law of thermodynamics and the law of conservation of energy, that if they can figure out what the heat is of a water substance in a container, they can use it to figure out what the heat or the specific heat is of a specific metal. Alright, so you make a note though, a device for measuring heat flow is a calorimeter. So your book gives you several examples of them. The middle one in this diagram that's the common one your book uses over and over and over again. So that's a constant pressure calorimeter. You don't have to know the others, your book's just pointing them out. Alright, so what do we do for this? So the scientists have decided that if we have a calorimeter like this, we can use this to measure the heat flow of a metal. Because remember, first law of thermodynamics, that if you have the heat of a system, if it's losing or gaining energy, that means it has to be able to absorb it from something else. That's how come if you have the energy is lost in a system, that means that the surroundings must be gaining it. And so that's what those equations are coming from on page 82. That you can't have energy just go into poop into nothingness. Energy just changes form. So energy loss has to equal energy gains to where it's just changing forms. So if you have it in a system where you have the system's losing energy, that means that the surroundings are gaining energy. Or if you have the system gaining energy, that means that the surroundings are losing energy. Like if there are ice cubes in the glass. If the ice cubes are gaining energy, that means that the water around them is losing energy. So you can't have the ice cubes just gaining energy from nothingness. It has to be coming from something. So, since we're taking this equation, Q equals Cm delta T, then we can actually substitute it for this equation and say, okay, instead of talking about, okay, if a piece of metal, for example, lost 25 joules of heat to the water, that means that, okay, if I chunk in a piece of metal into a calorimeter, that the hot piece of metal lost its heat into the water around it. So if a piece of metal lost 25 joules of heat, that means that the water gains how much joules of heat then? 25. So instead of using it like that though with heat, because very rarely do we ever have it that known, instead of using it as negative Q equals positive Q, since Q equals Cm delta T, we're going to take this equation and substitute it out. So it becomes negative Cm delta T equals positive Cm delta T. So that's where the equation on page 82 is coming from, to where it's the energy lost by the metal typically. That energy is absorbed in the water in the calorimeter. So what they'll do is they'll toss in a piece of metal, typically, and they will measure the temperature of the water. They'll know how much water is on the inside of the calorimeter, and they'll heat up the metal to a certain degree, and then they'll chunk the piece of metal into it. Alright, as I chunk my piece of hot metal into the water, the temperature of the water will start to rise. You can't see it really well probably, but the temperature is starting to rise. Now, once they have thermal equilibrium where that temperature doesn't change anymore, the scientists know, okay, that's it. They're at equal temperature. So that means that the water is at this temperature, but the piece of metal is also at that temperature. Once we know the mass of the piece of metal and the temperature change, we can use this to find specific heat of the metal. Because we already know what water is, 4.18. We already know the mass of the water since we measured it to put it into the calorimeter. And we can know now, okay, we knew water's initial temperature, but now we know and see, okay, how much it's stopped at. And so because of that, we can use this equation to figure out the specific heat of a metal. Since metals are a lot of pieces defined, or they have exact specific heats, they can use this to identify a piece of metal if they don't know what it is. They can actually use this to figure out what kind of metal that they have. Alright, so just make a note though, a device for measuring heat flow is a calorimeter. We'll talk through the math over how to solve this tomorrow again. Alright, so your homework for tonight. Read pages 83 to 85, so not a lot of reading, but 83 to 85. Answer on page 85. You're going to answer the questions. I think you should be able to do it. Let me check really quick. Yep, you can do it. Application 1 and 2. So application 1 and 2 on page 85. So just the first and second one. So application 1 and 2 on page 85. It's not working with calorimeters yet, so we'll practice with calorimeters tomorrow. But just make sure that you know how to do it. So try your best for it, and then pay attention in the reviews tomorrow or in the class review. So that way, if you get stuck, you know what you did wrong. Alright, so read pages 83 to 85 and answer the application 1 and 2. Alright, I hope you have a great day, and I hope you have a good rest of the day. I was about to say see you tomorrow, but